Okay, so good morning. I'm Giulio Ferrari, and these other people are the collaborators on this work. And the work has been mainly made in Modena between different institutions in Italy. Basically, what I want to present you is the model for a real sample that are core shell nanowires. I will show you the model we use to simulate the results where we apply a modulated magnetic field. I will show you the results and the emergence of Aharonov-Bohm oscillations. So first of all, since this is a broad audience, I tell you something about nanowires. So what are nanowires and a brief history of nanowires. So this is the first paper where nanowires were, the growth of nanowires were reported. So we have a semiconductor substrate. We put a catalyst on top of the semiconductor, and by throwing atoms of the same semiconductor under the drop of gold, in this case, the nanowire grows. And this was made in 1964, and then in 30 years, this is the results which have been obtained. But nowadays, we are able to grow better samples where we can control the position, the size of the nanowires, and also the orientation of the nanowires. And most important for us is that we can modulate the growth of the nanowires in a way that we can change the composition of the nanowires while we grow it. So it is possible to have quantum dots. Since this is a one-dimensional system, then modulating it, we have zero-dimensional systems. But what I want to focus on today is the modulation, the radial modulation. So you have a nanowire that is the core, and then you can grow different semiconductors around the core. So you have shells of different semiconductors around the core, as shown here, in a way that the carriers, the electrons, are confined in one of these shells. So you have a two-dimensional system, a two-dimensional electron gas with a prismatic shape. So you have your electrons on a 2D shell around a core. And this is the system we want to model. So, okay. So here are other examples of the same system. And here are two of our models. We have made a model for the prismatic core shell nanowires. But what I want to present you today is something simpler that is a cylindrical model, but that allows us to apply magnetic field, homogeneous magnetic field, but also modulated magnetic field like this. These systems are important, and it is important to underline that the dimension of these systems allows us to see quantum physics, because the radius of these nanowires are of the order of tens of nanometers. So they have the right dimension to explore quantum effects. On the two, so we can consider these two-dimensional systems. For example, carbon nanowires, single-wall carbon nanowire, are very much smaller, so they are basically one-dimensional systems, while here we are able to study this as real two-dimensional systems. What is common about these two systems is that the surface is not flat, but is curved. So we have a two-dimensional surface that is curved. And if you want to study the dynamics of carriers, of quantum particles on curved surface, you have to be careful, since this two-dimensional surface curved is embedded in a three-dimensional space. So the dynamics is not so obvious. And this has been studied since a long time, I would say 52 years, starting from the paper of David, and then going on until the last formulation of Da Costa of almost 30 years ago. And the important point is that if you consider the surface curved in a three-dimensional space, what appears is that you have an effect due to the curvature. So this last term here on the corner here, so this is the Schrödinger equation, normal Schrödinger equation, including the metric tensor, but it's just the Schrödinger equation. Then you reduce it to a two-dimensional surface. by a formulation explained in these papers. And what you have is that you have a effect due to the curvature of the surface. This is true for the dynamics on curved surface without fields applied. If you want to apply a field, it's even more complicated, because once you apply a magnetic field, of course, maybe that since the magnetic field acts on the velocity, and maybe you have an interplay between the curvature and the velocity. And so you have to develop, again, very carefully the theory. You start from the Schrödinger equation again, and then by the pair substitution, you include the magnetic field. And so you can see that there's a connection between the dynamics given by this operator and the magnetic field. And then you do again all the derivation that have been shown before. And what we obtained just last year is that this is the result. There's nothing to understand apart the fact that choosing the right gauge, you can demonstrate that the magnetic field and the curvature act separately. So you have an effect due to the curvature and an effect due to the magnetic field, and they don't have an interplay. But this is true only if you choose a particular gauge depending on the geometry. If you do not choose the proper gauge, you have an interplay between, or at least in the formula. Of course, then this is, we show that choosing the right gauge, you can demonstrate that there is not an interplay, physically an interplay between the two facts. So we have developed the general equation for any curved surfaces with electric and magnetic field. Electric field is not a big problem. The big problem is the magnetic field. And we want to apply it to this simple geometry that is a cylinder. So we have nanowires. We model it by a cylinder. And what we do, we apply a modulated magnetic field. So you have a magnetic field perpendicular to the axis of the cylinder that is modulated spatially. And here you have the proper choice of the gauge, and then the Hamiltonian written here. And what happens is that you have two parameters that drive your dynamics. One is the ratio between the radius of the cylinder and the wavelength of the modulation. So this determines your dynamics. And the, let's call it like a coupling constant between the field and the motion of the electrons. That basically is the ratio between the magnetic flux through a plaquette here and the flux quantum. And so we can simulate this equation. And these are the results. Here I show you the density of states as a function of the magnetic field applied, the intensity of the magnetic field applied, and the energy. So what we see is that the varying the magnetic field, you have energy levels that oscillates. They group into braids, and they oscillate. And the oscillation is the Aharonov-Bohm oscillation of energies. So basically, you have fluxes piercing your plaquette through. Why? Because if we look at the states, this is the modulus of the wave function on the tube. What you have is that your wave function has this shape. So it's concentrated in 4 dots. Let's call this 4 dots. And then these dots are linked by regions where the wave function is different from 0. So basically, you have a ring that is not a ring because it's more or less squared, and in a region where where the electrons cannot go, where the magnetic field goes through. So basically, Aharonov-Bohm configuration. And varying the intensity of the magnetic field, you see the oscillations. So here I've shown you also slices through the density of states to show that varying the magnetic field, we have a modulation of a change in the density of states of the system. You can change the radius of the nanowire, of the shell of the nanowire, or the modulation of the field. And what you obtain is that your density of states changes, but you still see these oscillations. If you take, let's say, you keep constant the spatial modulation of the field and you increase the radius, what you have is that basically you have strips. Otherwise, if you decrease the radius of the nanowire and you keep constant the modulation of the field, you have rings around the nanowire. But they stay in these regions where the component of the magnetic field perpendicular to the surface is 0. So we have seen a lot of rings built by lithography. Here, the interesting thing is that once you're able to grow these core shell nanowires, you don't need additional lithography on the system. What you need is a field that varies in the space. So, of course, is an alternative way of creating an Aharonov-Bohm ring. Just a couple of considerations about the symmetry, because you have seen, well, you know that if you consider the oscillation of the energy in a ring, I mean a ring, a round ring, what you have is that the energy oscillates like this, okay? So you have a continuous spectrum. While here you see that we have gaps between 4 levels oscillating, and this is due to the symmetry of the ring, because it's not round, but it's basically squared. And we have shown this on prismatic core shell nanowires, where we apply a field along the axis, and we have shown that the energy groups in braids where the number of levels oscillating depends on the symmetry of the system. And this is true also for these systems. This is not something completely new, because there are other systems which have been studied by other people, other groups, where the symmetry of the wave function determines the number of levels that oscillates. This is a self-assembled quantum ring where you have where the wave function has this shape, where you have 2 lobes, and the energy levels oscillates grouping in 2. That is exactly, you can see that these 2 results resemble each other. So it's exactly the same system. This explains also why the energy grows, because here you can see that the energy always goes to 0, while here the energy grows because you don't have really a one-dimensional ring where the particle is completely excluded by the center, but growing the magnetic field, the particle tends to go into the center, so the energy grows. When you apply magnetic field, the other thing that appears is Landau levels, and we have Landau levels in our systems. So I removed the density of states. I just left the energy of the ground state to show you that here we have the Aharonov-Bohm oscillation, but at some point in our spectrum appears that these energy levels that grow linearly. And these are the energy corresponding to Landau states. This is the energy of a Landau state, let's say, without the modulation, but with a constant magnetic field. And we can show that these energy levels correspond to wave function located not where the field is 0, but where the field has its maximum. So these Landau levels correspond to states where the wave function locates in dots in this region where the field has its maximum. So that's basically all. Maybe you think that these curved systems are exotic, but they have been built in different shapes. You can see these pictures also in a poster here at the conference. So real cylindrical systems have been built. There are, and we have studied this system in different configurations, also with a tilted magnetic field. Systems where you have a Y junction have been built, and we have done some simulation on the transmission, on the dynamics without magnetic field, but just to show the effect of the geometry of these systems. But you can build even more exotic systems. So that's all. What I've shown you is that we want to simulate real systems, which are core shell nanowires, where the electrons are confined in one shell, in a 2-dimensional shell. And I've shown you that which are the formulas that you have to use, the right Schrödinger equation that you have to use to simulate this curved system with magnetic field. And I've shown you the results where the electrons, the carriers, are confined in Aharonov-Bohm rings by the field itself. So that's all. Thank you. Well, we didn't put the spin-orbit interaction now. This is, by now, just a single particle simulations. The step we are making is to consider exciton on this system, so electron-hole pairs on this system. But we didn't put the spin-orbit interaction up to now. Maybe another step.
I remember going through the Bryce DeWitt paper about the Schrödinger equation of the curved space. And there was some controversy over an additional term related to the curvature scalar. I was wondering if you came across that and had to deal with it.
You mean
So
this one?
You didn't have it in your, so you've got your Schrödinger equation.
Yeah.
There's a sort of potential term that he has in his formula that relates to the curvature scalar. I
Yes.
was wondering if you...
Yeah. We still have the term related to the curvature,
yeah.
but
Because that was controversial. Some people were...
yeah. I know that. That's the point. Okay, the derivation has been made formally correct for quantum mechanics. The point is, can we show an effect related to this scalar potential? Our answer, that's the reason why we simulated this system, because this system can be a key experiment to show if this scalar potential due to the curvature is real or not. So here you maybe in these systems, the system that I've shown you, maybe there is not the crucial experiment, but maybe this one is the right system to show this. So.